Okay. Okay, the meeting's now being recorded. So thank you everyone for joining the IEEE Microwave Theory and Technique Society Santa Clara Valley, San Francisco Joint Chapter Tech Talk for the month of April 2021. The talk will be on a persistent autonomous monitoring system for timely detection of wildfires, also known as PANTHER. The speakers will be Dr. Katia Obraczka, Professor of Computer Science and Engineering at the University of California, Santa Cruz, and an IEEE Fellow. Andrea David, a PhD candidate at the UC Santa Cruz, will also be presenting. I'd just like to go over the agenda. We're going to go over a few meeting notes, COVID-19 update or situation with regard to our chapter meetings. I'll introduce the MTT Santa Clara Valley SF officers. Then we'll go into the speaker's bio and the talk. We will have question and answer within the talk and at the end. And then at the very end, stick around for the introduction and announcement of our May chapter talk. So a few things to note. This meeting is being recorded and we're using Zoom, of course, live. Links to the video recording and the slides will be emailed to registrants. We're keeping cameras and off and microphones muted to help deal with bandwidth issues and background noise. There is a raise your hand button in the reaction button area, and when the Q&A sessions points, which we may come to, you can raise your hand, and then we will be able to unmute you to ask your question. We ask that you ensure that your Zoom display name, which you can change, matches the one that you use to register. This will make it much easier for us to check you in. We do need to actually do this as part of our chapter duties, really, to record the attendance with regard to registrants. So please give us a hand with that. So the Institute of Electrical and Electronics Engineers advances technology for humanity. The IEEE and its members really inspire a global community through highly cited publications, conferences, technology standards, and professional and educational activities. And the society of which is hosting this talk is the Microwave Theory and Technique Society. And we focus on the theory and application of radio frequency, guided wave, and wireless technologies. Support us by becoming a member. You can join the IEEE at IEEE.org, and you can join the Microwave Theory and Technique Society at MTT.org. You can also find us on LinkedIn with the hashtag MTT-SCV. So with regard to COVID, all in-person meetings related to our chapter are canceled. Our monthly technical meetings, this one, and our officer meetings, which we hold monthly, will continue in online format until further notice. The 2021 chapter officers are as follows. The chair is Utkarsh Unikrishna. Myself, Tom McKay, as I am vice chair this year. Our secretary is Venkata, and our treasurer is Tan. So I'd like to introduce our speakers. Professor Obraczka is Professor of Computer Science and Engineering at UC Santa Cruz. Before joining UCSC, she was a research scientist at the University of Southern California's Information Sciences Institute and had a faculty appointment in USC's Computer Science Department. Professor Obraczka's research interests include computer networks, distributed systems, and Internet information systems. Her Internetwork research group at UCSC conducts protocol architectures research for wireless IoT, sensor, and disruption-tolerant networks. She has been principal and co-principal investigator on projects sponsored by government agencies such as the National Science Foundation, the NASA, DARPA, and others, as well as for companies, well-known companies like Cisco, Google, and Nokia. She is associate editor of the IEEE Transactions on Mobile Computing and the Association of Computing Machinery Letters in Computer Science. Professor Obraczka is IEEE Fellow and recently received the Santander Chair of Excellence and the INRIA International Chair Awards. Andrea David is fourth-year PhD student at the University of California, Santa Cruz. Her research interests include low-cost, energy-efficient IoT systems, distributed systems, wireless sensor networks, and their applications to environmental monitoring and emergency alerting. Andrea is currently working on her PhD thesis regarding the design and development of an autonomous, time-sensitive, large-scale and resilient IoT system for detecting and predicting wildfire events. Today's presentation is an Internet of Things system for persistent and autonomous wildfire monitoring, PANTHER. Destructive wildfires have caused catastrophic damage in California and many parts of the world. They are anticipated to grow in frequency and intensity due to climate change and urbanization. Existing methods face challenges in persistently monitoring large, remote areas before fires become large and difficult to contain. PANTHER, a low-cost, large-scale, energy-efficient IoT system deployed in remote areas, is proposed to monitor for conditions conducive to wildfires, their growth, and to support mitigation and preparedness efforts. PANTHER consists of clusters of mini weather stations collecting information about the surrounding environment and relaying that information through a wireless network to collection sites. Our presenters will describe PANTHER's design and system requirements and share initial power consumption results key to a viable implementation. Andrea, I'm going to stop sharing and you can begin.
Hey, thank you, Tom. I'm going to share my screen. Does that look good?
When you get to full screen there. And yes, I think Professor Obraczka was going to begin, is that right?
That's right, Tom. Thank you very much for the introduction and thank you all for attending our talk. It's a great pleasure to be here talking about our research to you all. And as Tom introduced us, this talk is going to describe our current research project on designing, implementing, validating, and deploying an IoT system for persistent and autonomous monitoring of wildfires. So this is the roadmap of the talk. I'll get started with some introductory remarks and some background on existing systems and methods. Then based on that, I will talk about our expected contributions and the design challenges that we face. And based on these design challenges, I'm going to then talk about the design principles that guided our design. And then Andrea is going to take over and then talk about the system's hardware and software, as well as our preliminary evaluation results on the power consumption of the system. So, we all live in California, and I guess I don't have to really motivate why it is critical that we try to monitor wildfires in a more persistent and autonomous way, and of course effective way. This slide is showing some pictures of the current wildfire season in 2020. In particular, for example, I don't know if you are aware, but the Santa Cruz campus had to be evacuated in the summer because of the CZU lightning complex fire. And actually, fortunately, the campus was pretty much evacuated already because of COVID-19, but still there were people that there are people that live there and had to be evacuated. So and the fire came close. I guess it was like 1 mile north of campus, so it came really, really close to our campus. So it is, you know, really a real and present danger to all of us in California. And in fact, 2020, you know, is considered to be a mega fire year. I think it was the first time that, you know, we had these kinds of statistics in terms of the area burned and also the, you know, the cost in suppression efforts and of course the structures burned. So the fact of the matter is that while wildfires are a natural phenomenon, and actually it's interesting because talking to an environmental scientist the other day, when I said that to him, he said, well, it depends on who you talk to, right? So, but the problem is that even if you consider wildfires a part of nature, right? The problem is that they have become more frequent and more intense, and of course more devastating, especially as, you know, human occupation, right, percolates into these wildland areas, right? So the question of the WUI, the wild urban interface, being you know, stretched to the max. So again, it's something that, you know, we really have to try to address and very urgently. So of course there are existing methods and solutions. For example, if you see on the lower left side of the slide, this is what you know, it's kind of you know, funny, but this is what firefighters use in their day-to-day activities. It's what they call the belt weather kit, which is rather primitive. But if you look at the right-hand side, there is a, you know, more technology savvy systems like these, you know, remote automated weather stations. And there's also more recently, there has been the installation of these high definition cameras that have been installed both by PG&E and SCE in Southern California, as well as this other network of cameras, HPWRAN, which is actually used by one of the systems that I'm going to talk about in a little bit. The problem here is, even with, you know, if we talk about these automated weather stations, the problem is that they are very sparse, right? And then they don't cover, their coverage is very limited. Next slide, Andrea, please. So then, you know, more recently, there are these other systems that have been proposed, like UC San Diego, together with the San Diego Supercomputing Center, they developed this system called Wildfire. And by the way, the little numbers, you know, close to the names are references, and at the end of the presentation, we'll have the full reference if you guys want to look at these papers in more detail. But, you know, Wildfire is basically a cyber infrastructure that assimilates all this data that is available, especially satellite data and data from these cameras. And then they feed that into their models for wildfire, real-time wildfire spread prediction. then there's this other system by UC Berkeley, Fuego, which is also another system that assimilates data from geosynchronous satellite, and then again feed that data into their own real-time wildfire spread prediction. And then more recently, I guess, yeah, there you go. More recently, there have been these other systems that have been proposed, like Planet Labs is also another system that was proposed by some UC Berkeley folks. And basically their idea is that they have sensors on the ground, and these sensors, depending on what they're sensing, they will trigger these satellites to start collecting images, and depending on what they see, alert emergency responders. And then another system, Fire Weathernet, which again uses on-the-ground sensors to sense the environment and then relay that information through a single sync node, through a data collection site that will then send that information onto the internet. So given these existing systems, again, the goal of our project is to try to mitigate the devastating effects of wildfires in terms of their societal effects, environmental, economic, and of course, health consequences for the population, and essentially complement what existing systems already provide in terms of data by providing in situ continuous real-time and more importantly granular data from these very remote areas, so the granularity is really the key point here, right? Not just the temporal granularity, but also the spatial granularity. And the system has been designed, as we are going to talk about in a minute, such that this spatial temporal granularity can be adjusted over time based on things like the application needs, as well as the current system conditions. For example, the battery levels on the nodes. So the system has this closed feedback loop that adjusts itself based on both the needs of the application in terms of how frequently they need to sample these conditions, depending on the different levels of alarm, so to speak, and also based on the system itself, its current battery life, for example, conditions. Of course, a system like this brings up a lot of design challenges, right? Again, it has to be low cost. It has to be robust in terms of being able to withstand the conditions on the ground, and then and of course, it will be deployed in situ, right? So we also need to determine where to place these stations. And of course, energy efficiency is a big deal, given that the system is going to be deployed and left unattended for arbitrarily long periods of time in these remote areas. So the system has to continuously operate and monitor these large outdoor areas and collect temperature, humidity, soil moisture, etc., information about the environment, all of which are important variables to detect conditions that are prone to wildfires. And like I said before, as it does that, it also needs to adjust to the different environment conditions as well as application requirements and conditions about the system itself. So based on these challenges, the main principles that guided our design are listed in this slide. Again, energy efficiency is a big deal, and we address energy efficiency both in hardware and software. In particular, we use what we call a hierarchical architecture, where we have, clusters of nodes, depending on the type of node, they will perform different functions, and I'll talk about that a little bit more. And of course, they have to be able to operate off-grid, so both in terms of power and communication. So the question would be what kind of communication technology to use, like for example, Wi-Fi versus LoRa. And of course, it depends on the requirements. Like, for example, LoRa, it will probably work depending on the type of data that you want to send. But for example, if you want to send video, then LoRa probably is not going to work for that. And so there is this trade-off, right, between long range, energy efficiency, and bandwidth. And of course, we will have the system be solar powered, again, to enable off-grid operation from the power grid. And then very importantly, modularity and scalability. As I mentioned before, the system needs to scale to be able to be deployed in very large areas. And the way that we address that is using modularity. So we have this concept of clusters that are sort of self-contained, so that you can expand the coverage of the system by deploying additional clusters. And then the system would itself self-organize and make these clusters interconnect and be able to not only sense the environment, but also take this information out of the environment through the network out to the internet eventually, right? So the system is not just sensing, but it's also being used to as the communication infrastructure for this the sense information to be carried across the network towards the internet, again assuming that these areas are not covered by existing communication infrastructure. And of course, reliability and robustness are very important. Okay, so now this is a figure that is trying to illustrate this hierarchical approach that we are using in order to scale the system and be able to incrementally deploy it. As you can see in the figure, we have these circles that are denoting the clusters. And then inside each cluster, you have these different nodes. The blue nodes are the sensor nodes, meaning the nodes that are equipped with the sensing devices like temperature, humidity, wind, etc. And then the red squares are what we are calling the cluster heads, which are basically there to collect information from the sensor nodes. And then the cluster head themselves are the ones that will relay this information through the network towards a data sync. As you can see that antenna there, the data sync is, we assume that the data sync has connectivity to the internet, so that the data is available broadly. So again, two types of nodes, the sensor nodes and the cluster heads. And again, the hypothesis there is that, again, this has to be a low cost network and potentially could be deployed in very large areas, and therefore we would need many of these nodes, right? So in order to keep them as low cost as possible, what we are doing is that we are trying to get these sensors to be very low cost, very anemic, so to speak, in terms of their capabilities, and then have these fewer nodes, the cluster heads, that probably would be more capable nodes in terms of their power capabilities and also their communication capabilities. So that's what this slide is saying. And again, the sink is this data collection site that ultimately will receive the data collected by the cluster heads and then relay that to the internet.
That code directly to C. So that C code can be then reused in AVP, like wrapped into a...
Sorry. So I think we're going to stop here because now we're transitioned to Andrea, who is going to talk about the more of the details of the system. But we wanted to just briefly pause and see if anyone has questions.
Right, thank you, Professor. So if you have a question, you can go to the bottom of the screen and you see a little smiley face that says reactions. And if you click on that, you can say, raise your hand like I'm doing right now. I have a question. I think, you talked about some earlier systems and, UC Berkeley, UC San Diego. Can you say anything else about collaborators on this project? I know, as an example, the way I first learned about your project was through, the KSBW Channel 8 down here in our region. And, CAL FIRE was, Chief Larkin, I think his name is, was part of the interview. So Katia, could you share with whom you're collaborating and maybe how?
Absolutely. And I again, thank you for, bringing this up because I completely forgot about that. So this project, we've been trying to collaborate with different, stakeholders and also scientists. Clearly, Andrea and I are not fire scientists, right? So we have a collaboration. We are collaborating with fire scientists at Berkeley, for example. We also, I'm not we are not showing this in this presentation, but one addition to the system that we have been thinking about is to actually add UAVs that would be dispatched on demand in case we need to have better sensing coverage and also communication coverage of these areas. But of course, because UAVs are also power limited, they cannot be flying all the time. So they would be stationed somewhere and then they will be dispatched triggered by the system. So in order to do that, we also collaborate with a colleague of ours at UC Berkeley that is whose specialty is UAVs and UAV operation. And as Tom pointed out, we have an ongoing collaboration with CAL FIRE, which is very instrumental because not only we talk to them about these sensors, but we also talk to them about the deployment, right? And our first target deployment is going to be at the I don't know if you guys have heard of I actually never heard of it before, and it's very close to us. It's called the SoCal Demonstration State Forest, which is an area that is run by CAL FIRE. Over in the Santa Cruz Mountains. So that's where we are planning to have our first test deployment. Actually, Andrea is going to talk about that later in the talk. So I hope but Tom, to your point about the existing system. So our hypothesis is that PANTHER is going to complement these existing systems by providing this on-the-ground network that is persistently monitoring the conditions with the spatial and temporal granularity needed in order to be able to detect these conditions, hopefully before the wildfire starts, or even if the wildfire starts, but before it becomes too big to contain.
Got it. So I see we have two other questions or hands raised. So I'm gonna go to Jehan. So I think, oh, oops, sorry. Try it again, Jehan.
Good evening. Ma'am, my question revolves on whether this model is applicable to a more non-urban like a forest, like where it is not very close to cities and which has not yet been properly explored properly. And if not, what do you think will be the challenges that this model will have to adapt to have that possibility?
Absolutely, and thanks for the question. Yes, so we, the system has been designed so that it is completely autonomous in terms of not needing to be close to any urban development, for example, to be able to access existing network infrastructure or even power. Right, so that's why one of the goals here of the design is to have a system that is it can operate off the grid, both in terms of the power and also communication infrastructure. So the system is going to be its own communication infrastructure, and it will be able to relay the data collected by the sensor nodes using these cluster heads, as I was describing before, so that it's completely independent of any infrastructure. And of course, it will, the deployment is going to be such that it will be eventually in one of these cluster heads will be eventually in range of a data sink that will be connected to the internet. I'm not sure if I answered the question though.
Well, maybe the question is, what would be an example data sync that, I mean, it looks like a cell tower or something, or maybe some kind of tower, and well, but it's actually, was the data sync part of the remote deployment, or is it?
Yeah, so for example, we can take actually we have to go visit the Socal demonstration forest, right? But in the Socal demonstration forest, I'm pretty sure that they have a place there where they have a data sync, so to speak, that would be connected to the internet, right? So okay. That is sort of what we have in mind. Or for example, CAL FIRE probably has stations, right, in these remote areas, but of course they are not dense enough, right, to provide coverage, the necessary coverage that we would need for the network itself. So that's why the network is self-sufficient in terms of relaying the information through itself until it reaches a data sync that then can be.
I think I understand. The clusters could be like daisy chain perhaps. So let me go to the next question. We have several questions now. So the next person in line is Gila.
Can you guys hear me?
Yes.
Yeah.
Awesome pronunciation of my name, Tom. Thanks. So I had two questions. One is, do you know what the deployment of these sensor nodes would look like yet? And two, usually fires are happening when the weather conditions are quite hot and the power grid is quite taxed. So does your plan consider if power outages are occurring?
Great, thanks for the question. The questions. Actually, Andrea is going to talk a little bit about the deployment plans later on. But as I mentioned before, one of our target test deployments would be in this demonstration forest that CAL FIRE manages. And as Andrea is going to show, right, we have an idea of how these clusters are going to be deployed there, so to provide enough coverage and also enough sensing coverage and enough communication coverage to be able to operate sort of independently. And then communicate, so relay the data through the network to the station in the forest.
So the data sync then would need to be resilient to power outage.
Right. And then the system. So if the data sync is connected to the power grid, right? Then if the power with power failures, then it may not be able to operate. But I'm pretty sure that these CAL FIRE stations probably have backup energy power sources, right? But the network itself can operate off grid, right? Because it will be solar powered. And that's actually, what we're going to talk about towards the end of the talk is our initial evaluation of the power consumption of these clusters and the nodes and the cluster head, and how do we make it more power efficient going forward.
Okay, we're gonna go now next to Utkarsh.
Hello, my question has to do with, I'm a little hazy about the significance of temporal and spatial granularity that you mentioned. It seems that it is something that is valued in your system. Can you just briefly explain what exactly that means and why it's so significant?
Because, the current methods and the current systems that exist are very sparse, right? They are not, you have these weather stations that have been deployed, but they're pretty sparse, over these remote areas. And, again, for you to detect, and this is actually something that we've been talking to CAL FIRE about, right? That there is really a need for more granular monitoring of these conditions, both in terms of spatial coverage and temporal coverage, so that these conditions can be detected, or conditions that are prone to wildfires can be detected in closer to real time, so that they can not only try to prevent these mega fires from happening, but also manage the dispatching of their crews accordingly, right? So the granularity of the monitoring is really an important component for CAL FIRE, for example, first responders, as well as even fire scientists, to be able to study these events and also historically make a connection between these events, their frequency and intensity, and also climate change, for example, right? So there is there is a more sort of immediate need, right, for collecting granular information, and there's also this more longer term scientific need to be able to connect that with the changing climate. I'm not sure if I convinced you, but
did that answer your question, Utkarsh?
It did. Thanks.
Because, you know, again, just, you know, sort of complementing that, it's clear that whatever exists now doesn't work, right? Because, you know, these fires, you know, this, I mean, you know, see the mega fire in 2020, right? We clearly need, you know, a different solution that is more proactive, and also can measure or can monitor closer to real time, instead of, for example, relying on satellite, right?
We have another question from Jay Banwaite, and then we're going to go on and move to Andrea, I suppose.
So I just had a quick question. I apologize if you've covered this already, but how would you compare the pros and cons of a terrestrial-based system to a space-based system, like a, you know, like one of these small satellites? Yeah, so
thank you for the question. So again, you know, these satellite systems, I mean, of course, when you have these, you know, up and coming constellations, right? Maybe you have better coverage and in terms of not just in space, but also in time, right? But having these, but still having the system in the ground. Like, for example, one of the things that that CAL FIRE and fire scientists are, you know, consistently telling us is soil moisture is a big component of this, right? Because that's the fuel for the fire, right? And so measuring soil moisture and automatically getting this information out of the network instead of them going out in the field and kind of manually measuring them is very important, right? So that would be one of the sensors that we would be using. And that type of information is very hard to get from like remote sensing infrastructure.
Okay, great. Let's move on to the next portion of the talk. Thank you everyone for your questions. If you could put your hands down now, then we can know who's got a new question on the next Q&A.
All right, thank you for the questions. So I'm going to continue with more details about the PANTHER system, starting with the hardware considerations that we're planning. So the purpose of our study, what we're showing here, is to be able to test our design considerations before we actually deploy them in the field. So as Katia mentioned, we aim to have a good trade-off between application requirements and energy efficiency, but also cost. So to this end, we propose 3 design categories, namely the low-end, mid-end, and the high-end design. And we want to be able to draw comparisons between their strengths and weaknesses in order to ultimately realize our final design of hardware choices. So in the low-end design, we assume that only the cluster heads are equipped with the camera. And the reason why, because the cameras are usually the most power-hungry components of our systems. And the cluster heads have access to more power and are deployed in fewer numbers than the sensor nodes. So this design would assume that the sensor nodes are equipped only with scalar sensors. So for example, temperature and humidity sensors, soil moisture, and even wind sensors. And the advantage of this design is that it's very energy efficient, and it's also relatively low cost in terms of deployment. However, the disadvantage of the design is that it doesn't quite adhere to our application requirements because we only would have visuals in regions where the cluster heads are located. And depending on the deployment, the cluster heads might be located very sparsely. So to help mitigate this limitation, we propose a mid-end design where we incorporate a camera module on each sensor node in addition to scalar sensors, and of course, in addition to every cluster head being equipped with the camera. So this design allows us to have nodes and more eyes on more regions, which conforms better to our system's requirements, but in turn, it requires more power from the sensor nodes. And of course, this is a more expensive deployment as well. So the addition of the camera module would greatly increase our chances of detecting wildfires in a timely manner. However, it does still have its drawbacks depending on the cameras that we decide to use. So if you use visible light cameras, then we cannot capture images in the dark. And even with night vision cameras, they still need some small amount of ambient light to be able to create images. And it is known that shadows and smoke can easily prevent the night vision cameras from obtaining a valid image. So to address these issues, we proposed a high-end design where we consider incorporating a thermal imaging camera on every cluster head, in addition to day and night cameras and scalar sensors on the sensor node. So with the thermal imaging cameras, we could detect differences in heat from hundreds of feet away. And we could also capture precise temperature readings day and night as well. So this design would offer a more robust solution for our application needs. However, it does have, of course, a big disadvantage that due to the price of the thermal imaging camera and also their power requirements, this design is also the most expensive out of the three. So in this table, we summarize the specification of the different hardware components for each PANTHER design category. So in the low-end design, we consider using fairly low-cost, off-the-shelf components that are popular in many home electronics projects. And this design would allow us to have an easy and relatively inexpensive deployment of our first sensor node prototype. In the mid-end design, we consider using a little bit different components. They are a little bit pricier here. But however, with this increase in price, it also comes with some advantages. For example, quicker response time or more accurate and wider range of measurement. And of course, this design would include a camera module on every sensor node as well. In the high-end design, we consider using FLIR's thermal imaging camera. And as you can see, the price of the camera is much higher than any of the other sensor nodes combined. And the response time of the camera is also fairly slow, and it does have a very high power consumption as well. So again, this design is very expensive both in terms of cost and power efficiency. Regardless of the design, we would include a radio transmitter and a radio receiver on every node. And for our sensor node CPU, we consider using a Raspberry Pi Zero, just in case we want to add a camera module on it. But for the cluster head CPU, we consider using a more powerful single board computer, such as a Raspberry Pi 3. And the reason why we want something more powerful on the cluster head, because in addition to being able to pre-process some preliminary data before we send it to the sink, we also want to be able to run some machine learning or some other algorithms on this node. So we need something that is capable of supporting that. So in this presentation today, we're only going to be focusing on the mid-end design. So later on in the evaluations, we're going to be showing using parameters from the components in this design. So moving on to the software design, we'll show you how nodes form and maintain clusters. And we'll also discuss trade-offs between energy efficiency and application requirements in terms of our dynamically controlled duty cycles that Katia alluded earlier. And this is also a big feature of our system as well. So once the nodes are deployed, they are left unattended and they are responsible for forming clusters by themselves. So our clustering approach uses two phases, very similar to the leech protocol that's cited later in the slides. But the two phases that we use are namely cluster formation and cluster maintenance. The cluster formation phase occurs only once when the network is first deployed. And in this phase, the nodes organize themselves into clusters and establish an initial schedule that is TDMA based, where each sensor node is assigned a slot to communicate. So this TDMA-based schedule will be later maintained by the cluster head as part of the cluster maintenance phase. But during network operation, the nodes in the clusters would follow this cluster schedule, and the schedule will also repeat itself in rounds. In the next few slides, we'll show how this TDMA-based schedule is created and also how it is maintained.
Andrea, by TDMA, you mean time division multiple access, am I right?
Right, correct.
All right.
And I'll show you a picture of the schedule, so hopefully this explains it a little bit better. So cluster formation happens as follows. So when the nodes are initially deployed, the cluster heads would initiate the cluster formation by broadcasting a discovery message to all sensor nodes within range. So this discovery message would contain the cluster head's identifier, which is usually its IP address. And it would also contain the current time that is used to synchronize the sensor nodes clocks based on the cluster head's clock. It would also contain some information about the time when the next round of the schedule will start. And this is so that the sensor nodes will know when they should turn on their radio and listen to the cluster head. And I'll explain later on more about that. So when the sensor nodes hear the broadcast from the cluster heads, they save all of the identifiers from all of the cluster heads that they heard from, and they put it in memory. And they choose to send a join request to the cluster head who has the strongest received signal strength. So it's usually the closest cluster head, but it doesn't have to be that the case. So once the cluster head hears from a join request from a sensor node, it sends back an acknowledgement that contains the sensor node's assigned slot number. And the slot number is based on the first served basis, meaning that the first slot in the schedule will be assigned to the sensor node from which the cluster head heard from first. However, the cluster head cannot accommodate the sensor node. It will not reply to the join request. It wouldn't send an acknowledgement. And in that case, the sensor node will wait for the acknowledgement until the next round of the broadcast. And if it still doesn't hear back from the cluster head, then it will try to go and select the next cluster head who had the next highest signal strength and so on. And then it will try to send a join request to that cluster head and try to join the cluster. The cluster formation phase concludes at the start of the next broadcast or at the start of the next round of the schedule. And at that moment, the TDMA-based schedule is fully established with assigned slots for the cluster head and each of the sensor nodes that were able to join the cluster. So here in figure 2, we show the TDMA-based schedule, again, time division, multiple access based. And so here, the first slot is usually allocated to the cluster head and followed by all of the sensor nodes. But at the last slot in the round is allocated for the cluster head, the C forward, so that it can aggregate and pre-process information from the sensor nodes and allow time to relay it to the sync. So this schedule will repeat itself in rounds and will be maintained by the cluster maintenance phase. So the schedule will keep repeating until all of the nodes in the network would exhaust their energy. The cluster maintenance phase begins once the cluster schedule is fully established. So we have this established TDMA-based schedule where each node knows when it should transmit. And this cluster maintenance phase, unlike the cluster formation phase, it repeats itself periodically. So the cluster maintenance goes as follows. First, the cluster head would broadcast a beacon message at the start of each round of this TDMA-based schedule. And this beacon message would, as opposed to the discovery message from earlier, it would inform the sensor nodes about the duration of the cluster head's slot interval. And this is important because this is when the sensor nodes will know that they need to have their radio receiver turned on for the duration of the cluster head broadcast. And any other time they can have their radio receiver turned off because that would prevent overhearing and also reserve energy. So knowing the duration of a cluster head slot, the sensor nodes will know how long they need to keep their radio receiver on. The beacon message would also contain the current time, again, used to synchronize the clocks of the sensor nodes. And it would also contain information about when to expect the next beacon message. So basically telling the sensor nodes that they need to turn on their radio receiver next time so that they can hear the cluster head's broadcast and hear if the cluster head has some special instructions from them. So the beacon message, in addition to serving as a way to inform the sensor nodes about the schedule or any other information, it also serves as a keep alive message for the cluster head, so that the sensor nodes know that their cluster head is still operational. So for example, if the sensor nodes don't hear a beacon message from their cluster head for a predetermined amount of rounds, they decide that the cluster head is maybe unavailable or it exhausted its energy. So they will try to connect to another cluster head and try to join another cluster. So once the sensor nodes hear the beacon message from the cluster head, they will turn off their radio receiver again to prevent overhearing and also to conserve energy. And then the sensor nodes would take turn transmitting information to the cluster head based on their assigned spot in the schedule. So when it's the sensor node's turn to transmit information, the first thing that it would do is it wakes up all of its sensor components and waits until all of them are able to take information from the environment. So waits till their response time. And then it collects data about the environment and takes this information and transmits it to the cluster head. Once that's done, the sensor node would turn off its radio and all of the sensors and just go to sleep so that it would reserve power and it would be in sleep mode until the next round and the next turn to transmit. So once the last sensor node slot interval concludes, the cluster head would aggregate the information received from all of the sensor nodes in the cluster, and then it would relay this information to the sink, where the first responders or fire personnel can look through the data and decide what to do. But it would send this information through the network of cluster heads. Usually if the network is large, then it would use a routing protocol to route all of the information to the sink. So this cluster maintenance phase will keep repeating until, again, all of the nodes in the network deplete their energy. So during cluster operation, PANTHER can also adapt its duty cycles, as Katia alluded to it. And it adapts the duty cycles based on the current environmental conditions that are sensed by the sensor nodes. So duty cycling is a very well-known method for where nodes periodically turn on and off their sensor components. And it is widely used in wireless sensor networks and also in IoT to save power. So although duty cycling results in energy savings, it can also negatively impact the performance of the network. So it can increase the latency with which we deliver information to the sink. So if the sensor nodes are need to collect information from their environment, but they are in low duty cycle mode where they sleep, we're not going to be able to get information until they're back on operational again. And also another thing that can impact the performance of the network is having them duty cycled a lot. We would decrease the data freshness and the accuracy of the data that they collect. So to achieve a good trade-off between application requirements again and power efficiency, PANTHER enables two modes of operation, which is the normal mode and the alarm mode. So the normal mode is employed, normal mode employs an energy efficient duty cycle, so for monitoring the environment. So this is usually where the mode where the sensor nodes and the cluster head would be operating. But alarm mode is activated when there are conditions that need to be relayed promptly to the sink. So for example, if the sensor nodes sense higher than normal temperature readings, or they sense something in the environment that can be conducive to wildfire initiation. So that's when this alarm mode is activated. So in the next few slides, we'll show in more detail the two different mode of operation of both the cluster head and the sensor node. In terms of the cluster head's duty cycle, we assume that regardless of the mode of operation, the CPU and the radio receiver of the cluster head is always turned on. So this is so that the cluster head can hear any incoming messages at any given time. And we wanted the CPU to be on because we wanted to be able to process information in the meantime. However, as you will see in the evaluations later, having the CPU on at all times actually gives us limitations in our power efficiency. It is the dominating factor in our evaluations, the power consumption. So eventually we want to duty cycle the CPU as well, but for now we consider that it is always turned on. So the cluster head's job in normal mode is to transmit its beacon message periodically, and it would receive and respond to join requests from any sensor nodes that want to connect. So at any time, if you want to expand the network or add more granularity to the data, then we can just deploy another sensor node and it can connect to the cluster head very easily. And the third thing that the cluster head does, it aggregates information from all of the sensor nodes in its cluster, and then it takes this information and transmits it to the sink. However, in alarm mode, the priority of the cluster head is to transmit information to the sink as quickly as possible. So nothing else matters in that alarm mode. And how it would be activated is that as soon as the cluster head senses that has an information from the sensor node, their elevated temperature readings or any other conditions that are outside of normal, then the cluster head would send a beacon message to the sensor nodes to tell them that now we're switching to alarm mode and that they need to have their sensors turned on and they cannot duty cycle them anymore. And the reason why we don't want to duty cycle in alarm mode, because we want to be able to just collect information from the environment as quickly as possible and send it towards the sink. So this would cut out the time it needs for the sensor components to turn on and be able to collect valid information. In that case, if they're always on, they can just quickly collect the information and send it without needing to wait for their response time. In alarm mode, also, the cluster head doesn't respond to any join requests. Again, the priority is to just transmit information that's currently available to the sink, and then the cluster head can later on deal with the join request. If once the cluster head determines that the conditions are back to normal or that firefighters came out and they were able to resolve the situation, then the cluster head can decide to go back and switch back to normal mode. So the sensor node's duty cycle in normal mode has three states. It has the listening, the sensing, and the transmitting state. So in the listening state, it happens in the very beginning of the schedule where the cluster head is broadcasting information to them. So in that state, the radio receiver of the sensor nodes is turned on. And once the cluster head finishes broadcasting information, then all of the sensor nodes turn off their radio receiver and switch to the sensing state. So in the sensing state, the sensor nodes would wake up all of their sensors, wait for the response time for the sensors so that they can collect valid measurements of the environment. And then later they would collect information about the environment, turn on their radio transceiver and transmit this information to the cluster head. And then again, they would turn off their radios and their sensors and then would go back to sleep until their next turn. However, in alarm mode, again, the priority here is to just get information from the environment as quickly as possible. So the sensor nodes would keep all of their sensor components turned on and also would keep their radio turned on as well, just in case they need to hear some new instructions coming from the cluster head. Again, the sensors are never turned off because we want to be able to get the information from the environment very quickly without needing to wait for the response time of the sensors. It can be a few seconds, but it can also be up to a minute, as we've seen from the table. And the next thing that they do in alarm mode is that they collect information from the environment and send it to the cluster head. And that's it, they just wait for the information from the cluster head where they can actually switch back to the normal mode and start duty cycling their components again. So we want to be able to evaluate PANTHER's power consumption in terms of the two modes of operation, the normal mode and the alarm mode. And we also want to see how duty cycling the sensor components can help reduce our power consumption. So we characterize the power consumption of PANTHER using CUJA, which is a popular sensor network simulator and emulator, and it's usually used to evaluate low power and resource-constrained Internet of Things devices. So there are a few assumptions that we make here with the evaluation. The first assumption that we make is that the cluster heads and the sensor node CPU is always turned on. So as you'll see later in the evaluation results, this actually increases our power consumption because the CPU does dominate. So eventually we'll be able to decycle the CPU. But for now, we consider that they're always on. And another assumption that we make here is that the sensor nodes cannot reconnect to another cluster head after their cluster head dies. So as soon as their cluster head depletes its energy, the whole cluster is lost. And of course, that can lead to limitations of our system. So we're working on developing that part of the system as well currently. But again, for now, we assume that once a cluster head dies, the sensor nodes cannot reconnect to another cluster head. So for our initial deployment, we partnered with CAL FIRE, and we want to be able to install PANTHER at CAL FIRE's SoCal Demonstration State Forest, which is a forest that spans 2,681 acres, approximately 4 miles in Santa Cruz. And the deployment size and the number of the clusters will depend on the deployment of the granularity and the granularity of the data that we wish to collect. And of course, also the transmission range that we can achieve with Wi-Fi or other communication methods. But here in the simulation experiments that we conduct, we assume that we're going to be using an antenna and that the communication distance for the cluster head can reach up to 1 kilometer and up to 100 meters for the sensor node. Another assumption that we make here is that although our design includes both rechargeable batteries and also solar powered cells, here in our simulations currently, we assume that we have a non-rechargeable power supply of 6,000 milliampere hours. And this is approximately equal to 2 AA batteries. And the reason why we chose that power supply is because typically weather stations that are on the market and you can buy online are powered by 2 AA batteries. But of course, later we can increase this capacity, as we'll see from the evaluation results. Again, we want to simulate that there we have a non-rechargeable power supply because we want to see how long our nodes can last in the field. So simulate the worst case scenario. So we also characterize power consumption in 2 different deployments. We characterize using a single cluster deployment and also multi-cluster deployment. So the reason why we want to do a characterization of a single cluster and a multi-cluster because we want to be able to see how the components contribute to the energy consumption in a single cluster topology. And then we also want to be able to simulate our network in a more realistic situation where we consider the SoCal Demonstration State Forest as the area that we like to cover. Similar to the network lifetime, so this is a metric that we use to evaluate the power efficiency of our system. And there are a lot of different definitions of the network lifetime that exist. And we came up with 2 definitions for our metrics here. And the reason why, because our goal was to see how long does it take for the first sensor node to deplete its energy in a single cluster topology. And the reason why, because if one of the sensor node dies in the cluster, then the neighboring sensor nodes can just take over and provide coverage. However, in the multi-cluster topology, if one of the cluster head depletes its battery, then it can result in the whole network becoming disconnected. So not only the sensor nodes will lose coverage, but also routing might also be impacted. So this is the reason why we use 2 different definitions of lifetime. In the single cluster topology, we consider the network lifetime to be the time it takes for the first node to exhaust its energy. And in the multi-cluster topology, we consider the network lifetime to be the time it takes for some fraction of the total number of nodes to become disconnected from the network. So for the starting with the single cluster topology, we consider a cluster of 5 sensor nodes, like in the picture below. And we assume that these 5 sensor nodes are connected to a cluster head, and this cluster head is communicating directly with the sink. So there is no routing involved in the single cluster topology evaluation. So the figure here on the left shows the results of the energy consumption of the sensor nodes and the cluster heads component-wise. So in the normal mode of the cluster head and also the normal mode of the sensor node, we can see that the CPU is actually the one that dominates the power consumption. And since we had this assumption that the CPU is always on, we weren't actually expecting this to be the dominating factor, but it is. So this tells us that we do need to duty cycle our CPUs to be able to achieve better energy consumption measurements. Here we see that although the camera is the most power-hungry component of our system, in the normal mode, it has fairly low energy consumption since we're duty cycling this camera. However, we see in the alarm mode that since alarm mode has all the components turned on, right? So the camera is actually consuming the most power, which makes sense because it has the highest power consumption out of all the components on the cluster head. So it shows that it does make sense to duty cycle our components here. Similarly, with the sensor node, in normal mode, again, the CPU dominates. In alarm mode, we can see that the radio is also increases energy consumption since it's always on. And we can see that the wind sensor dominates the power consumption, but the reason why, because it does have the highest power consumption. These results are very consistent with the table that we shown earlier. The results on the right show the lifetime of the PANTHER nodes, both in normal mode and in alarm mode. So the cluster head can last in a field about 9 hours without needing to recharge its battery, with not having the CPU duty cycled. As opposed to the cluster head, the sensor nodes can actually last about 57 hours in the field. So it's 6 times more than the cluster head. So this further shows that we do really need to duty cycle the cluster head, or that we need to add more battery capacity to the cluster head so that it can last longer in the field. However, these preliminary results are not quite bad because if we take in account that we're going to use solar power cells, then having 9 hours of battery life would be enough because it will get us through the night, which is approximately an average 8 hours. So we're hoping that the next day we have some sun and we can recharge our batteries for the cluster head. But again, here we see that we do need to duty cycle the CPU and that we do need to add more capacity to it.
I'm sorry, I'm confused. It seems like normal mode and alarm mode are swapped here.
So in normal mode, in the figure on the right?
Yeah. You have longer lifetime. Oh no, sorry, never mind. You're right.
Right. So normal mode does have longer lifetime because we're duty cycling most of the components here. Yep. In alarm mode, the cluster head with this preliminary measurements, it can last about 3 hours when the sensor node can last about 11 hours. So far it's okay because we're hoping that in 3 hours, we can get the firefighters on the scene and be able to check out the area. But of course, we can always add more capacity to the battery that we are using. So with the multi-cluster topology, we want to be able to evaluate a more realistic scenario where we have multiple clusters communicating with each other and be able to cover an area of the size of the whole SoCal demonstration state forest. And here from the picture with our preliminary experiments, we see that it takes about 8 to 9 clusters to be able to cover an area. So this is the amount of clusters that we started experimenting with for the multi-cluster topology. So here we're showing the results for the network lifetime. Again, that's the percentage of the total nodes, the time it takes for the percentage of the total nodes to become disconnected from the network. And here we see, so remember that here we assume that the sensor nodes cannot reconnect to another cluster head once their cluster head dies. So here, both in the normal mode and both in the alarm mode, we can see that for 100% of the network to die, it takes about 9 hours, and in alarm mode, it takes about 3 hours, which is consistent with the lifetime of the cluster head for the one cluster topology. And the reason why is, of course, because since the sensor nodes cannot reconnect to another cluster head, if their cluster head dies, then the whole portion of the network will become disconnected. So again, this is another reason that shows that we need to duty cycle the CPU on the cluster head, and also to be able to experiment with ways where the sensor nodes can reconnect to another cluster head. So this is part of our ongoing and future work. We're working on evaluating the power consumption by duty cycling the cluster head sensor nodes in CPU. We also want to perform experiments on larger cluster sizes where sensor nodes are able to reconnect to another cluster head. So hopefully we'll get better measurements with the multi-cluster topology and the lifetime of the network. We're also planning our initial field deployment at UC Santa Cruz on a small scale, where we just evaluate our, with small size clusters, we evaluate some real world deployment in our sensor node prototypes. And then eventually want to test at SoCal State Demonstration Forest with a larger deployment and with control burns with the help of CAL-FIRE. Great. Well, thank you for listening. At this moment, we're happy to take any questions or comments that you may have. Here's our contact information, and also here are our references. I'm sure these slides will be available, so you can look through those.
So we have a question from Yuan Liu. You need to, there you go.
Oh, sorry. Yeah. Hey. Well, first of all, let me say I'm very excited to see this type of project. Yeah, I came from my previous employer was a IoT company that did a very different application with their own technologies and so on. So one of the questions is, how interested are you in cooperating with commercial entities? But that's less relevant. So I have several more technical side of questions. Just get my notes. So I see one is the lifetime. When you say your say cluster head dies in 9 hours, does that mean every 9 hours some person needs to go in and replace battery, or does it mean you have some other compensation mechanisms?
So the idea would be, thank you for the questions. The idea would be that we would have solar power and also rechargeable batteries. And of course, having bigger battery supply for the cluster heads. So we would rely on solar power to recharge these batteries. And here we see that we're able to last about 1 night without solar energy. But if we extend our battery capacity, then we can accommodate for multiple days where it's not very sunny outside. So yes, we are planning to be able to recharge these batteries and leave these nodes in the field unattended completely and have them be operational for multiple years.
So another one is about the actual deployment. There are two considerations I want to ask about. One is the manpower. You mentioned that each sensor node range is like 100 meters, and each cluster head is about 1 kilometer. So in terms of deployment, that means the manpower consumption is going to be rather high. And another factor is more on the right of way. How will you acquire that right of way to deploy these sensors?
Okay, let me try to answer the first part of the question. So yes, we want to be able to communicate on longer distances, and you're right, the power consumption for that it will be higher. Depending on the radio that we use, for example, if we use Wi-Fi, then it's going to be fairly expensive in terms of power consumption. But there are some other communication methods, such as the LoRa radio, which is relatively low power. Since we want to be able to transmit both video and just very small amounts of information, like just quick information from the environment, readings from the sensors, we consider using maybe even 2 radios. So one radio would be the very low power radio for just transmitting scalar sensor information, and then being able to have maybe Wi-Fi to only transmit video when needed. You had the other part of the question, I think maybe I would refer to Katia. You also had a question with cooperating with companies. So maybe let Katia respond to that.
Yeah, so regarding collaborating with companies, of course, we are always, open to doing that, given that, we are really trying to make an impact and sort of build a real system. So we are always open to collaborating with companies. Yeah, so by all means. And I think that the other question was regarding deployment, right?
Yes.
So what we are hoping to do is that by collaborating with CAL FIRE, right, we would be able to, they would be able to help us with deployment, right? They would be able to guide us in where we should be deploying these systems, at least, for, test deployment and proof of concept purposes, right? And so once, we kind of validate what we are doing in the field, right? Then I guess, the next step would be to maybe, go into mass production and then think about more automated deployment methods. For example, I have another student that is working on optimizing placement of sensor nodes in outdoor applications that consider terrain, so that you can maximize coverage, right? Including, coverage from visual sensors like cameras, right? So we there are, these other sort of, related projects or research that we can probably relate to, the deployment question, right? But as of now, what we are targeting is this, these test deployment sites that we will conduct with the help of CAL FIRE.
Oh, okay.
So they are going to be so basically it's going to be deployed in a much more controlled manner, right? Guided by them.
So yeah. Thank you, Yuan. I want to move to a question from Jeremy, as he hasn't had a chance to ask a question. Then there's one more from Jahan. And Yuan, thank you very much for your enthusiasm, and seems like there's an opening to reach out by email. So I'm going to go ahead and unmute Jeremy.
Thank you. Yes, this is very exciting. As a resident of Santa Cruz, I think it's pretty important too. I also had a question regarding deployment and placement. In the SoCal demonstration forest, how many sensors do you plan to deploy in total?
Andrea, do you want to show your map?
Yes, that's a very good question. So again, it will depend on the granularity of the data that we wish to collect. And it will also depend of just the communication range that we decide on using. So right now I am showing the cluster heads. It has about 9 clusters on the map, and I was with communication range of up to 1 kilometer that I was assuming earlier. We have about 9 clusters. In regards of the sensor nodes, again, it will depend on the granularity of the data that we wish to collect. So if you want to have very precise information from multiple areas, then we would deploy more sensor nodes. But I think for the start, we'll just try to experiment with smaller numbers at first, and then see if you need to scale it up.
So what sort of order of magnitude are we talking about? 100 nodes, 100 sensors in total, or 1,000 sensors in total? I mean, sort of ballpark magnitude number.
Right, I think a hundred number of somewhere in the hundreds is a good ballpark.
Okay, so I assume that each sensor is able to be individually identified when a message is pulled back to the data sink. So for example, you could have sensor, it'll be cluster head 4, sensor 6. Is that correct?
Yes, that is correct.
So that then leads to the question, when the message arrives at the data sink, how does the data receiver, or the human receiver, how do they determine the physical location of where that message, where that sensor originates? Does the sensor have its own mapping algorithm that can identify where it is, on the planet, on the surface of the planet, or is that determined by the initial deployment?
A very good question. So yes, we would. The algorithm video is very good too. Maybe have even a GPS module on the sensor nodes so that they can know their location exactly and transmit that as well with the data.
I see. That sounds but that's something that's envisaged for the future. Presumably that doesn't exist in your currently considered experiment. Is that correct?
Yes, not at the moment, but yes, it's definitely something for the future.
I see.
And
Okay.
So just adding to that, so like, the sensor, the cluster head could actually have a GPS sensor in it. And given that the sensors are not, the network is not moving, right? You would just need one, one reading of the GPS information in order to be able to locate the where these nodes are, right? So, yeah.
That is certainly true. But then again, I'm thinking, obviously this probably wouldn't be the case for this deployment because it's an experimental deployment. But I think, if this was used in, if this was deployed in a 100 square mile forest, then I would imagine that sensors could move through animal activity or through inadvertent or malicious human activity, or there could be. There could be sudden debris flows from rainfall, depending on how they're placed. I mean, there could be movement, possibly, but I agree with you. Yes, you wouldn't need that GPS data to be pulled on a sort of hour by hour or even second by second basis. That could be much less frequently.
Right. But yours is a very good point. Absolutely, because location is important in this particular application.
Yeah, and I'm not a fire scientist, but I could imagine that there are certain topological features could cause fire funneling or could cause particularly nasty fire artifacts, and so one might want to have a knowledge of that from your sensor deployment. I mean, I was envisaging a sensor deployment where you would sprinkle these things from an airplane.
Exactly, yeah. So that is sort of the ideal situation, right? That eventually we, would be able, or will try to be able to do that. But then you would have to have some form of mobility of the sensor so that they can actually, move to where they should be. Right. And actually this algorithm that I was mentioning from this other student actually assumes that, you can either, place the sensors, or the sensors can actually move on their own and position themselves if they have mobility, mobility capabilities.
Wow, that's exciting. Okay, thank you very much. Thank you for the presentation.
Oh, thank you for the questions and for attending.
So we have one more question from, Akarsh has a question as well, but we'll go to Jehan again.
Thank you, Andrea, for the presentation. My doubt is a bit more on the shape of the nodes with relation to the cluster node, because is there like an optimum shape? Have you of like how many nodes in your area would you like to have, or like would it be like the center, the cluster would be like a center of a hexagon or a pentagon like that? Have you considered optimization in terms of the mesh of your nodes?
Oh, that's a very great question. Yes, I think that's the next thing to do. I know in our lab there are a few people developing algorithms for that. So yes, it's the next step to consider. Right now, we're just using a star topology where, again, the sensor nodes are directly connected to the cluster head. But yes, it's a great question. Eventually, we would need an algorithm to determine the optimal placement.
On a similar note, is it necessary for each node sensor to have all the sensors? You could maybe only have a mesh of temperature and then soil. Like those ways of optimization, are you also considering?
Yes, that's also another way to look at it. Since we're going to have many sensor nodes, we might not need as many sensors on them. So yeah, one of the sensor nodes can maybe just have temperature and humidity, and the other ones maybe even sensors and have them be nearby. But yes, or we can also run algorithms to have determine if the wind didn't really change direction in a while and didn't change speed, maybe we don't have to have the wind sensor turned on every time the sensor node needs to transmit its information. So yes, we can also do it in hardware, and we also can do it with software, with some algorithms.
So so this is actually known as, data aggregation in sensor networks, which is a way to, save energy by aggregating data. And then, for example, in this case, you would aggregate data in time, right? So that if you have, very close readings, then you don't have to send them all the time if things are not changing, right? So you can do some local aggregation in the sensor nodes themselves and also in the cluster head in order to be able to save energy. So that's another, these are other strategies for energy conservation. Very good point.
Thank you, ma'am. I have just one last one. How would you, similar to what the previous speaker was saying, how would you avoid a false positive? Like, for example, someone doing a campfire there.
So the question's about false positives. Thank you, Jehan. Then we're going to go to Hesham and then Akarsh.
Yeah, so I think we're going to first look at the information. So we are also going to look at how the wildfires are spreading. So let's say there's one particular sensor at the very left corner of the field is sensing the higher temperature readings, also soil moisture very low. Then we'll see if it really spreads to other sensors, if the other sensors can also detect it. And maybe we can flag that to as go investigate, or we can have different levels of urgency when we're sending information. But again, we also looking at not just information from one sensor, but from multiple sensors, and seeing seeing what direction, if there is a fire, what direction it is moving. But if there isn't a fire, and again, it's a false positive, then we're also going to look at where is it, are any other sensors also experiencing this, or just that one sensor in a very popular tourist spot or camping spot maybe.
So you can so as Andrea was saying, you can actually have like the camera, for example, disambiguate, right? Depending on the information, but in fact, you may wanna detect campfires because they are actually important causes of wildfire, right? So depending on where you are, campfires are not allowed. So maybe, the first responders would like to know if a like a not allowed campfire is going on there. So
yeah. Okay, so thank you, Jehan. I'm going to go to Hesham. We're running significantly over time, and I really think the interest is great, so don't want to cut things off too short, but we also would like to wrap up the meeting. So I'm going to go to Hesham now. Hesham, you should be able to unmute now.
Yeah, I have two simple questions. Number one is why you choose TDMA scheduling algorithm?
So, Andrea, do you want me to answer that?
Oh, sure. Yeah, I can add to it.
So that is actually a very good point, and the reason for doing that is to try to avoid collisions as the sensor nodes are transmitting data to the cluster head. So because we would know ahead of time the membership of the cluster, and there is a natural central point of control, right? Then we chose to do a TDMA style data collection within the cluster. That way, we assign the slots to the sensor nodes, and then we avoid collisions in doing so.
Yeah. And my second question, which should be quick, why don't you use a network like the one provided by Sigfox to connect to the head and all the nodes in a cluster?
I'm not familiar with this technology that you mentioned.
I think it's quite similar to LoRa. I think LoRa and Sigfox compete. Am I right, Hesham?
No, it is not LoRa. It is a special protocol provided by Sigfox.
Okay. So is there an advantage to the Sigfox protocol that you could highlight?
I connect all the sensors and the head using a Sigfox network, which is made specifically to connect IoT devices and sensors, like sensors.
Okay. Right. Well,
yeah. The problem with doing something like that is that we actually wanted to I'm not sure. I am not familiar with this particular technology and protocol, but we want to avoid using proprietary systems, so that we can, for example, have access to, for example, doing a TDMA approach to collect the data, and also try to, duty cycle the different components of the system in order to save power. So that's why we are, choosing a more, open source, so to speak, design. But I think it's interesting. I think we should look into this technology to figure out what the specifications are in terms of range and bandwidth and power consumption.
But sorry, what open source you are using for this project?
So we, so again, we are using, so for the right now, our test deployment, so to speak, right? We would be using Wi-Fi.
Wi-Fi.
Yes. So thank you, Hesham. We need to move to the last.
Exactly. Thank you very much. I appreciate it.
Thank you for the question.
And I'm assuming you will send us the slides, right?
You will get a link to the slides and to the recording of the video.
Thank you very much.
You're welcome. Akarsh? Akarsh, did you have a new question? I'm sorry, I saw your hand was up. We can't hear you. You're unmuted, but we can't hear you.
Okay, can you hear me now?
Yes.
Okay, thank you. So my question is, how do you determine where to place cluster nodes and sensors? Like, is there an algorithm, or based on prior history of these sites? How do you decide that?
Yeah, so for our, quote unquote, controlled deployments, right, we will be guided by CAL FIRE, and specifically in the SoCal demonstration state forest, right, where they want us to, place those clusters. And based on that, then we will determine if the communication coverage is sufficient. So again, as you can see in this map that Andrea has there, we are sort of assuming that the nominal communication coverage of 802.11, right? But of course, it will be very dependent on terrain. So so that's why we have this initial deployment on paper, so to speak, right? But once we go and deploy in the real deployment site, right, we will be able to test if these assumptions are valid. But we will be kind of relying on CAL FIRE to tell us where we should place these cluster heads, and therefore, the sensor nodes around it for the first time. But then, as I mentioned before, we do have another research project in the lab, which is looking at, deployment algorithms that try to optimize connectivity and sensing range in outdoor areas, taking terrain into account. So for example, we could provide to this algorithm a height map, which is available from these, the shuttle. There is this shuttle project that sort of maps out the Earth in terms of height. So, providing a height map of the region at hand, then run the algorithm, and the algorithm will provide us the optimal placement of these nodes in terms of their coverage.
Very good. I think, Jehan, we have to have that be the last question, as we're about a half an hour over our normal time, and we want to thank our speakers for an awesome presentation and engagement with our attendees. Thank you very much, Professor Katia Obraczka and Andrea Davis.
Thank you all for attending, and also for all the interest. And please, feel free to contact us offline with questions, and we'll be happy to answer them and engage.
Awesome. So Andrea, if you could stop presenting, I'm gonna go ahead and share my screen again so that we can wrap up today's meeting with the announcement of, well, here we go. Venkata?
Yeah, I'm here. Thank you, Tom. I would like to thank Professor Katia and Andrea once again from our chapter. Thank you for your time, taking time to present your work. It's very interesting. With that, I would like to introduce our talk for the next month on May 19th at the same time, 6:30 p.m. to 7:45 PST. So the topic for the talk is History and Future of Implantable Antennas by Dr. Cynthia Forse. Dr. Cynthia is a fellow of the IEEE and National Academy of Inventors. She is a professor of electrical and computer engineering at University of Utah, Salt Lake City. And the abstract for the talk is that implantable medical devices now touch virtually every major function in the human body. Wireless telemetry for these devices is necessary to monitor battery level and device health, upload reprogramming for device function, and download data for patient monitoring. Emerging medical telemetry devices have led to recent advances in the design of small biocompatible antennas that can be implanted in the human body. The work on the paper will track the type of antennas seen in the past, the technologies that enable these changes, and prospects for future implantable antennas for medical applications. We hope to see all of you in our next talk, and thank you for supporting our chapter, and please join IEEE and support our chapter. Thank you once again. Have a good rest of the night.
Thank you, everyone. Bye for now.